visual reference to the ground is uncertain or impossible because of clouds or darkness of night, radio aids to aerial navigation enable the pilot or navigator to initiate instrument flight. In addition to his maps, charts, and the instruments of his airplane, the pilot can readily follow his flight plan with the aid of directions, signals, and information transmitted to him by radio from many points along his route. Air navigation radio aids, published by the Civil Aeronautics Administration, and radio facility charts by the Air Corps supply detailed information which facilitates full use of the various radio aids along the airways. After referring to the index on the back page of the handbook, the pilot then turns to the particular chart covering the section of airways over which he plans to fly. He finds many symbols along his proposed route, each serving as a definite marker and each involving the use of some portion of his radio equipment. Radio range stations, operated by the Civil Aeronautics Administration, are located at principal cities and at certain intersections of airways. Each radio range station serves as a directional aid to pilots. At most radio range stations, the transmitting antenna consists of 5 vertical radiators, 4 of which are located at the corners of a square, and the 5th at the center. Any 2 diagonally opposite radiators project the radio field, which is maximum along the axis of the 2 towers and minimum in the 2 directions perpendicular to the axis. If the letter A is transmitted over a pair of these radiators, the greatest signal strength is projected in line with the radiators. In code, A is dot dash. These dot dash signals are strongest at the point of transmission and get fainter as they get farther from the transmitter. When a second pair of radiators is placed at 90 degrees to the first pair, it projects a radio field of similar shape and at right angles to the first. The letter N is transmitted over this pair of radiators at the same radio frequency. In code, N is dash dot, just the opposite of the A signal. Thus, 2 distinct radio fields are established, intersecting at the point of broadcast. The signals transmitted by each pair of radiators are audible on each side of the axis of their greatest strength, getting fainter as they spread out. Let us examine 1/4 of the field. The 2 signals overlap perfectly, making a continuous tone or on-course signal at the line of intersection. This line of intersection, always giving the on-course signal, determines the location of the radio beam. When these signals are properly synchronized in transmission, they will interlock or mesh like the teeth of a gear. When both have the same tone and volume, neither can be distinguished, but instead a single monotone or on-course signal is produced. The continuous monotone established by the overlapping of the 2 signals takes the form of a long, narrow beam. It is bordered on one side by the so-called N zone, with the letter N being audible, and bordered on the other side by the A zone, with the letter A being heard. A radio beam, therefore, is a long, narrow directional beam with approximately 3 degrees spread located between the N and A zones. This map shows how the United States is covered by these ranges. For a short distance on each side of the radio beam, there is a space known as a bisignal zone, in which the monotone is heard but with the A or N signal distinguishable above that background. As a pilot departs from a beam, one letter becomes more and more distinct until the background monotone disappears. At the very edge of the radio beam on each side is a narrow border which is known as the twilight band. In this very narrow band, either the A signal or the N signal can be barely distinguished against the monotone background. If all signal fields are of equal transmitting strength, the four legs of the beam emanating from a radio range station will be at 90 degrees. Very often this is not desirable, since the beams would not correspond to the direction of the airways. The direction of the beams can be adjusted by increasing the signal strength of one field, which will impose itself upon the two adjacent fields and will result in a change in the direction of beams as desired. Directly above the antennas, or towers of the radio range station, there is a dead space where signals are almost inaudible. This is known as the cone of silence. This is a limited area shaped like an inverted cone, in which all signals fade. As an airplane approaches, the volume of the signals increases rapidly because of the proximity to the point of broadcast. As it enters the cone of silence, they fade abruptly. When it leaves, the signals surge back with great volume, then slowly diminish as the distance of the airplane from the station increases. Occasionally, while flying, a pilot may experience a momentary fading of the signals or a false cone of silence. This can be distinguished from the true cone of silence because of the absence of the surge of volume at the edges of the cone. The A and N range signals are interrupted every 37 seconds for the transmission of station identification signals, which consist of two letters in International Morse code. For example, the Memphis range station broadcasts its identification, which is PS. This signal is always transmitted in the N pair of quadrants first. If a pilot is flying some distance off a beam in the A zone, he will hear the A signal for 25 seconds, a pause, and then the station identification letters. But an airplane on the beam will hear the on-course signal for 25 seconds, a pause, and then PS from the N antenna, followed by PS from the A antenna. At most radio range stations, Z-type markers are installed. On a radio facility chart, the small triangle indicates the location of these markers. These markers are called visual cones of silence because they project a small unkeyed signal field vertically above the range station at the ultra-high radio frequency of 75 megacycles. These beacon signals may be received by an airplane passing overhead on a separate pre-tuned receiver, and as the airplane passes through this radio field, an amber panel light flashes. In this manner, the pilot has additional assurance that he is flying over a radio range station. The fan marker is another radio aid which assists the pilot in determining his exact location. Placed on beams at varying distances, such as 20 or 30 miles from range stations, it functions as a position marker. On radio facility charts, the exact mileage from each marker to the range station is indicated. Each chart produces a vertical, fan-shaped signal field extending across a beam and at right angles to it. The fan marker is keyed to signal its location by dashes. The marker located on the north or northeast beam gives off a 1-dash signal. The second, in a clockwise direction, emits 2 dashes, the third 3 dashes, and the fourth 4 dashes. These signals can be received visually on an aircraft receiving set and are transmitted on the same frequency of 75 megacycles as the station location markers. The pilot can distinguish the fan markers from the station location markers, since the fan markers are not close to stations and they broadcast signals of 1 to 4 dashes depending upon location. For example, the pilot can see the 1-dash signal indicating that he is over the north beam marker at Cuba. The 2-dash signal shows he is over the east marker at Fisherville. The 3-dash signal flashes if he is over the south marker at Coldwater, or the 4-dash signal if he is over the west marker at Hughes. Another radio fix or location marker is the intersection of radio beams. For example, a pilot flying from Waco to Fort Worth will start on the Waco beam at a frequency of 385 kilocycles. When he believes he is approaching the beam from Fort Worth, he will tune his range receiver to 365 kilocycles from time to time until he can pick up the on-course signals of that station. When he comes into the Fort Worth beam, a glance at his chart will inform him of his exact location. The pilot is further aided by his radio facility chart. It shows the range station symbol and indicates by shaded areas within the triangle 2 zones that are the A zones. In making an instrument flight on a beam, it is important to be quick in detecting the A or N signal, which indicates that the aircraft is sliding off. The pilot must be equally alert in making necessary corrections in flight direction in order to return immediately to the beam. On-course flying is not a difficult task, but requires the constant attention of the pilot. Assume that a pilot starts a flight from Fort Worth to Texarkana by instruments. He is aware that the beam is 69 degrees, directs his airplane at that angle, and attempts to hold to it. Very shortly, the pilot is aware that he is no longer on course because he hears the N signal with increasing volume. He realizes he is drifting to the right due to a brisk crosswind. To correct this, the pilot turns left to 30 degrees. This is a fairly large correction, but he realizes the importance of quick, effective action and the immediate return to the beam. It is apparent that this correction will be too great. The pilot intends to change direction to the right by splitting the difference between his original 69 degrees, which carried him to the right, and his corrected heading of 30 degrees, which results in approximately 50 degrees for his next course. The aircraft has now entered the A zone. The pilot knows he is now to the left of the beam and proceeds to turn right a few degrees. He decides upon 60 degrees, which splits the difference between the 69-degree course, which took him right, and the 50-degree course, which he is now following. He hears the A signal fading and knows he is approaching the beam. It is now apparent that he must make another correction, or else he will cross the beam to the right and slide off into the end zone. He continues his calculations by reasoning that a course of 50 degrees took him left of the beam, and his present course of 60 degrees will take him too far to the right. So he adjusts his course by splitting the difference, which is 55 degrees. His radio sounds the monotone, which tells him he is on the beam. Since his present course of 55 degrees is not quite correct, he decides upon a course of halfway between his present course, which is too far left, and 60 degrees, which was too much to the right. While on the beam at 57 degrees, he will split the difference between 55 degrees, which took him left, and 57 degrees, which is leading slightly to the right, and follow a course of 56 degrees, which holds him in the correct direction. The pilot has learned by a trial and error method the necessary correction for the wind on his left, which was an unknown factor, and is able to continue on the beam without difficulty. There are 5 common errors made frequently by inexperienced pilots in attempting to fly on a radio beam. First, when a pilot finds that he is flying off a beam and desires to make a correction, he may continue to turn. This will confuse him. It may cause him to cross the beam at a right angle. He should remedy his condition by making a series of moderate correctional alterations of his course and hold each until he can definitely establish his location. Second, when a pilot is off course, he may attempt to make quick changes of direction while approaching the beam, but before actually entering the beam. Unfortunately, because of reflections from or absorptions by mountains, high buildings, ore deposits, bodies of water, and so forth, there frequently will be found short auxiliary multiple beams paralleling and giving off the on-course signal. He may confuse these with the true beam and be led farther off his course. A third common error is the failure to utilize the relative intensities of the A or N signal. This can be overcome by holding the volume of the airplane radio receiver very low. In approaching a beam, it must be remembered that the A or N signals are hardly audible above the monotone background. Volume control must be manual, as the automatic volume control position will make courses wide. The fourth error is in making violent corrections in approaching the radio range station, at which location the beam is very narrow. It must be recalled that the beam near a range station is only a very short distance from the middle of a bi-signal zone. Therefore, any violent correction may result in an almost immediate reversal from a broad A zone to a broad N zone signal, thereby causing the pilot quite unnecessarily to zigzag his course or to become confused regarding the location of the beam which he has been following. Finally, the fifth error the pilot may make is a failure to consider the element of drift. A pilot must keep in mind a picture of the beam and visualize the effect the wind will have upon the actual direction that his airplane will travel. In flying within a radio range system, a pilot frequently must determine his location in relation to the range station. This is known as quadrant identification or radio range orientation. One method of identification is the 90-degree method. The pilot, hearing an A signal, knows he is flying in either quadrant 2 or quadrant 4. He determines the average bisector of each A zone on his chart and then turns to a course which is at right angles to that bisector. As soon as he crosses a beam, he makes a 90-degree turn, always to the right. If he again hears the A signal, he knows he is back in quadrant 2. He orients himself, makes a reverse turn, and easily locates the beam, following it to the station. If, however, after turning, he continues to hear only the N signal, he knows he started in quadrant 4. Thus oriented, the pilot makes a reverse turn and has no difficulty in aligning himself on the beam. Among other methods employed in quadrant identification is the parallel method. The pilot flies parallel to the average quadrant bisector, noting the fading or increasing in volume of the zone signal. If the volume increases, he knows he is approaching the station. Then, if he desires to reach a station, he flies parallel to the east leg until the desired on-course signal is reached and over the north leg of the beam to the station. In peacetime, regular hourly weather reports are transmitted by range stations to aircraft over the same frequency as the A or M signals and without interrupting these signals. At each radio range station, a fifth tower has been constructed for voice broadcast and used primarily for weather reports. An airplane flying by instruments normally is equipped with a small filter unit on the receiver circuit and a three-way switch on the instrument panel through which the pilot can receive the range signals alone, or the weather reports, or a combination of both the weather reports and a background of A or N zone signals. Another important navigation aid is the radio compass, which exists in several forms. The simplest of these forms is a radio receiving unit with a left-right reading indicator on the instrument panel and a fixed antenna loop. This is used chiefly as a homing unit. The pilot tunes this set to the radio station to which he desires to go and turns his airplane until the needle is centered. With this alignment, as long as the airplane is headed directly toward the radio station for which it has been tuned, the indicator hand remains centered. Any headings of the airplane to the right or left of the station result in a corresponding opposite deflection of the hand on the dial. Another type of radio compass, more inclusive in its construction, makes use of a loop antenna which can be rotated inside its streamlined case. This has all of the properties of the radio compass previously described and serves in addition as a radio direction finder. With the rotating loop, the pilot may obtain bearings without changing the course of the airplane. In direction finding with this type of radio compass, the pilot or navigator merely tunes the receiver to a given radio station. This may be either an official radio range station or a commercial broadcasting station. The crank which drives the loop and the bearing indicator directionalizes the loop antenna toward the broadcasting station so as to center the hand on the radio compass dial, With the hand in this position, the pilot looks at the bearing indicator where he takes a directional reading. The indicator arrow now points directly to the radio station. By setting the outer dial scale of the bearing indicator to the corrected magnetic heading of the airplane and reading the tail end of the bearing indicator pointer, the pilot or navigator can determine a bearing on his chart from north through the radio station to the airplane. Two or more of these bearings can be plotted to determine the position of the airplane. If the pilot is flying a beam, he can determine his location by noting the intersection of the line from a radio station and the beam on which he is traveling. The automatic radio compass is the newest addition for homing purposes or direction finding. Its loop antenna rotates automatically. Operation of this compass is simple. It is switched on, the proper band selected, and the desired station tuned in. Exact tuning of each station is evidenced by a maximum deflection of the tuning meter. When a station is selected, the antenna and the bearing indicator needle automatically point to the direction of that station. Turning the airplane to that direction will zero the needle. Pilots have learned that the art of flying an airplane over a course, with or without visual reference to the ground, can be mastered easily and accurately if necessary dependence is placed in the various instruments at their disposal, and if they will take the time and patience to familiarize themselves with the many aids that radio facilities offer.